I feel a bit of an interloper at the feast here. I accepted the invitation in good faith, explaining that I don't see myself as particularly working in either machine learning or personalised medicine. But as Neil says, there are, I think, always useful overlaps between cognate fields and philosophies, and I hope some of this will have some resonance with the audience. I could argue that for a fair bit of the talk, I am talking about localised medicine, in the sense that the underlying message is that as more and more health outcome data becomes routinely recorded and stored electronically, so there is a potential for us to interrogate those data in real time and inform local, whether it's in space or time or on an individual basis, local decisions about what the best thing is to do now. But certainly, as I think Neil was saying while I was being mic'd up, most of my work is concerned with population health rather than individual medicine. But the first of the three applications I'm going to talk about today is on an individual level, so I hope that's okay. So the context, as I say, is that we've got all this data pouring in, and certainly in the UK, in the National Health Service, much more data is collected and stored than is ever analysed. In my local hospital, they have very detailed electronic health records, but they only access them when somebody threatens to sue them, so that they can actually check that proper procedures were taking place. They don't use them for active monitoring of healthcare delivery. This can be relevant at different spatial scales, whether you're dealing with an individual or a community, or, as in my third area of application, whole countries. I've put real time in inverted commas there because it sounds very high-tech and jazzy. All I really mean is statistical methods for updating analyses as data accrue. And depending on the context, real time could actually mean monthly. All right? But in other words, rather than doing a study for 3 years and then seeing what the results are, you analyse the data as the study proceeds. In the work that I do, this is often in a geographical context, so you need spatial stochastic processes. And I think it's always worth bearing in mind when you're choosing statistical methods to address particular problems. One of the most basic questions to ask yourself is, are you concerned with prediction or explanation? Okay? And I think to some extent, most of us are concerned with both, but there's never a free lunch. And the optimal way to do prediction is not necessarily the optimal way to understand mechanisms in science. I'll elaborate on that if people press me to in discussion. So basically the talk is just 3 case studies, and the common underlying thread is that they all incorporate at their core a latent Gaussian process which measures the evolution in space or time or both of some phenomenon of interest, but the data that you have to actually tell you about that phenomenon are noisy, and therefore you don't have to, but my chosen solution to that is to build stochastic models so that to counter the fact that our data are noisy and we have an imperfect measure of what's really going on, we add assumptions. And those assumptions, incorporated in the latent Gaussian process model, buy us information. They buy it at a price because those assumptions are not necessarily innocuous, but that's the tension that seems to me to be inevitable when you're dealing with messy observational data. So the first of the 3 case studies is about kidney failure, and just to emphasize that this is not a trivial problem in the UK, these data are now unfortunately rather old, but you can see that there's been a steady rise of in UK mortality numbers attributed to kidney failure of the order of 15,000 a year towards the end of the last decade. And renal failure generally is a very insidious condition. It can be asymptomatic for many years, and although it's asymptomatic, you can actually measure it biochemically by taking a blood sample, measuring something called serum creatinine. And that serum creatinine has been developed as a proxy for the underlying state of a person's kidney. So in this rather unpleasant looking equation, on the left hand side you've got what the clinician infers as the state of somebody's kidney, and the key biochemical marker on the right-hand side is serum creatinine, and there's an adjustment for age and sex, which is clearly an oversimplification, but it gives a reasonable correspondence that clinicians are happy with. And so if people are at risk of kidney failure, then you can actually monitor the progression quite well, whereas if they're either not at risk or are at risk but don't know it, then they can basically go from being asymptomatic to a hospital case remarkably quickly, which is something you want to avoid. So the proposition here is that although most cases of kidney failure are irreversible, you can slow the rate of progression, principally by controlling people's blood pressure. And so the proposition that was put to us in Lancaster by some clinicians just up the road in Salford was whether we can actually use statistical modelling of these blood chemistry measurements, serum creatinine, to try to uncover people who are actually in the process of losing their kidney function to a point where some serious clinical intervention would be warranted. And the point about that is twofold. Firstly, as it says in the first bullet point at the bottom under treatment and survival, if you can actually slow the rate of progression, you give people many more years, you can give people many more years of good health without drastic intervention. But the second thing is that if you are having to sort of intervene, then you have to do a lot of planning, because the resources for what's called renal replacement therapy, which either means dialysis or transplantation, are very expensive, and in the case of transplantation, scarce. And so if you know what's going on, you can do more early planning of how you're going to cope with the need for aggressive intervention against kidney failure. Okay, so say our colleagues at Royal Salford basically say, in their clinical judgment, based on their experience, if they knew that somebody was losing at least 5% of kidney function a year, they would want them referred to secondary care. Okay? And they deal with data which, roughly speaking, consists of these EGFR measurements derived from that unpleasant equation. And if you log those, you can see from the form of that equation, the red equation there, that on a log scale, there really isn't any difference between EGFR and serum creatinine, right? There are some numbers there which are actually point estimates of parameters based on clinical studies, and they're almost certainly wrong in the sense that they were on a particular population at a particular time. So basically, you can use the biochemistry as being equivalent to the kidney function as long as you work on a log scale and you do adjustments for age and sex. Okay, there's quite a lot of data available to us to actually try to help our colleagues in Salford meet their clinical guidelines. In particular, we've got a database of nearly 23,000 people who are currently, well, not currently, these data are now, I mean, they're historical data, but at the time we did the analysis, there was a database of 22,000, etc., primary care patients who were at risk in the sense that they had comorbidities that were known to be associated with a high risk of kidney failure. Predominantly diabetes, but also there's quite a strong ethnic genetic variant in terms of susceptibility to kidney disease. Okay, and some of those people have had a remarkably large number of blood tests, up to 305. The median is 12, and the time span of the data is about 10 years of follow-up. And this is an extract from a remarkable resource called the Salford Integrated Record System, which collects in one place all of the primary and secondary care from the city of Salford in a form which in principle can be interrogated for analysis. I say in principle because, like any set of data relating to individuals' health, there are strong ethical protections, and so you have to go through numerous hoops to get access to these data. But every day that database is updated by downloads from all the healthcare providers in the city. So it's a very rich resource for this kind of work. And what I try to do as a statistician is turn a clinician's question into a question that I can phrase in terms of probability. Because I would venture to suggest, and I've got at least one colleague who has an opportunity to disagree with me, that if there's one thing that statisticians all agree on, is that the way to formalize uncertainty is through probability. Right? That's the right measure of uncertainty. So we turn the clinical guideline into a statement that says what you want to know is whether somebody's GFR, and notice that I shouldn't even have had, it seems to me, firstly, there shouldn't be an E on it, because eGFR is estimated glomerular filter, right? And it's noisy. GFR is what the kidneys are really doing. And you can measure it, but expensively. So it's not routinely measured. But what we want to know is whether that true GFR is decreasing at a rate of 5% a year, which on a log scale means is the derivative of that process less than minus 0.05. And it's conditioned on the history, so that every time you get a new measurement, you want to update that probability. Right, now this is another example of large scatter plots with low signal to noise ratio. On the whole of the database, if we look at the data cross-sectionally, in other words, we ignore any linkage of the time sequences on individual patients, you can see again that there's it's very noisy, but there is a perceptible downward trend. And there is actually a highly significant kink in the line at the age of about 60. Now, a split line is another approximation, but it's certainly true that all of you, your kidneys are failing, right? But almost all of you needn't worry about that, right? Because there's a lot of redundancy in the kidney function, and it's only when your kidney function gets down to about 20% of normal that you even start feeling ill, right? So, and certainly 50% is enough to keep people happy and healthy for indefinitely. But the kidneys do have a finite life. So if we cure all other diseases, we'll all die of kidney failure eventually, right? Oopsie daisy, a bit too quick there. When you look at the longitudinal structure of the data, you can see that there are sort of more complicated stories around that population average line. So that red line is what statisticians call the cross-sectional effect of age. The longitudinal effect of age can be different in different people. Some people actually maintain kidney function very well, and it can improve as well as go bad. There are all sorts of things that can attack the kidney if you're ill, your kidney function is compromised and so on. And the sort of people that the clinicians really want to detect, preferably sooner rather than later, are this person here, who you can see has basically been toddling along and is actually looking as though they're losing their kidney function pretty rapidly. So these are the people that we'd really like to try to identify. And we do it through what I call a dynamic regression model. It's no different to David's regression model with random effects. It's just another phrase for the same thing. We've got the data on these responses Yij, which are log scale GFR estimated. We model the expectation, the cross-sectional effect, as linear in initial age and time since recruitment. We do actually put a split line in, to be honest, so calling it linear is a bit of an oversimplification, but it's approximately linear. But the rate of progression varies randomly both between subjects and within subjects. It varies between subjects because of other things about them that we haven't measured. So that subject, that U there, is a random variable which represents all the things that I ought to have measured on that person to understand the state of their kidney function, but I don't have the data available. I just have their age and their sex. Okay? It also, however, varies randomly within subjects. As you can see from the data I showed you, although the overall population average is quite adequately modeled by a simple curve, the individual trajectories vary in all sorts of quite subtle and complicated ways. So that means we need a stochastic process, which is where the word dynamic comes in, to describe what's going on at the individual level. Okay, so we then write down our model, and notice there what we've got is the age and sex adjustment, okay, which we know from all the early clinical work matter. We've then got this split line formulation, and 56.5 there is another magic number. That's another point estimate that should really have a standard error attached to it. But compared to the stochastic variation at individual level, the errors in the estimation of the population level trajectory are negligible because I've got a lot of data, right? That would not give me good predictions of what's happening to an individual, but for the population average, I can more or less ignore standard errors of regression parameters. And so then on the third line of the model, we've got the random effects. We've got the individual level at which a person arrives in the study, which is the U, and we've got their time varying trajectory, which cannot be predicted by their age. There you go. Right. Now, with unashamed pragmatism, if you're trying to build these kind of models, you can go outside the Gaussian world, but life is so much easier if you're going to stay within the Gaussian world. And so it's an assumption that we know is usually an approximation, but it's way the most practical way to build models, at least initially. And if you can get away with it, you breathe a sigh of relief and off you go. So what we did is we tried various specifications for this stochastic process C of t, and eventually we came up with the best fit that we could get amongst the reasonably standard models at our disposal was an integrated Brownian motion. Now that was a happy accident because the clinical criterion of interest, as you recall, is about the derivative of the stochastic process. So whatever stochastic process we fit to the data, what we're trying to predict is what its derivative is currently doing. So modeling it as the integral of the thing we're interested in is certainly convenient. Of course, you can do that without assuming that B is Brownian motion. You can simply say C by definition is the integral of the thing I'm interested in. But it's certainly, the Brownian motion is a relatively simple model to deal with, because it basically says your best prediction of the future is the present, but your precision around that prediction, okay, necessarily and realistically gets more and more vague as your forecasting horizon increases. And all you then do is you just basically fit the model to the data, and you're done. So here's a largely uninformative table of parameter estimates, and as you can see, rather small standard errors. The interesting things for the prediction problem are the variance components, and you can see that the signal to noise ratio is pretty low. All right? Okay, so you've got this signal is the time varying, the variance of the time varying Brownian motion that we're interested in, okay, and this is the independent errors, normally distributed errors around, okay? And there's also a lot of between patient variation, which means that there are missing covariates that we haven't identified, but for estimating the derivative, that doesn't actually feature at all. So I've already shown you a few sample data sequences. Here are some more, that's I think that's not an unrealistic characterization of what these data look like. There are changes which are due to real biological events. There's a pretty high noise level in the assay, and there's a lot of heterogeneity between individuals. So using a time-honored statistical test called draw two pictures and see if you can see the difference, that's what simulations of the fitted model look like. And you can be the judge of whether, roughly speaking, that looks like it's capturing the right sort of behavior. Okay, all we now do is then just wrap that up into a prediction algorithm, and I'm just going to show you here 3 cases of very different kinds of trajectories that were in our data. A lot of them show what I would call the classic progression, which is that for a number of years you're losing a little bit of kidney function, but basically there's no need to panic, everything's doing fine. And then what happens is that the kidneys begin to tip over the edge, and the process accelerates, which is why it's the derivative that's actually of diagnostic value. And I'm sure you would all agree that if you were presented with all of the data in the left-hand plot, you'd want that patient treated. But if you could imagine just seeing the dots one at a time, at what point would you decide they needed refer? And by treatment, sorry, I do mean they're being treated in primary care, of course. I mean referred to specialist secondary care. And so in the middle panel, what we've got is our best point estimate of the current derivative, okay, and its confidence interval. And on the right-hand panel, we've got the predictive probability. So the kind of, if it's not too grandiose a word, philosophical point I try to make when I'm talking to medics about this is that I see my job as a statistician of computing that probability, and their job as a clinician of deciding what to do about that probability, because they told me what the criterion was that they would use if they had it, and I say, okay, on the basis of all the data you've got about this person, the probability that that criterion is being met is what I'm plotting there. Now, whether you intervene at the 50-50 call or you wait until it's almost certain will depend on many things, including, for example, the age of the patient, their general state of health, the scarcity of resources, and clinicians are paid large amounts of money to make those very difficult decisions. But what I would like them to do is make the decision based on the best estimate of what the signal's doing rather than noisy data, okay? I can tell you that the average standard of presentation in renal clinics is an Excel spreadsheet, and people eyeball the blood figures, and that's the best they've got. Okay, this is a classic presentation of somebody who's had a kidney injury. I've no idea, it might be a rugby player who's been kicked in the back, whatever, but what happens here is that there's been a catastrophic drop towards the end of this time sequence, okay, but the patient then recovers. And again, I mean, the algorithm does what I think you would want it to do. It suddenly says, oh boy, something really dramatic's happening here. And again, the clinician will know much more than there is in this model about this person, may then rush them off to hospital if they think their kidneys are failing, may simply treat the acute injury, and you can see that then things begin to get back to normal. Okay? Now, acute kidney injury can also signal something that basically means your kidneys are failing. This acute injury is not being recovered, and so what happens here is that we end up with essentially certainty that this person meets the clinical criteria for referral to secondary care. Okay, so that's, whoops, don't know how that happened. My own incompetence, I guess. So that's the end of the first case study. What I'd really like to do with this is field test it in clinics, and haven't managed to set that up. There's an interesting methodological point for the statisticians in the audience of informative follow-up, which is that the times at which people get their bloods taken are clearly related to their state of health. And all of this methodology assumes what's called non-informative follow-up times, meaning that you can what you measure can be predicted from everything that you've measured in the past, and it doesn't depend additionally on what you've not measured. Okay, that's a slightly convoluted form of words, but that's what it means. And so if you think about it in terms of mathematical statistics, what you've actually got here is a requirement to jointly model two stochastic processes. There's the GFR process, which you observe occasionally with noise, but there's also the point process of times at which GFR measurements are made. And there's no reason why those two stochastic processes should be independent, but my current methodology doesn't quite assume they're independent, but it assumes the dependence is of a form that means that you can actually reliably predict the future from the past. And the other point I wanted to make, although it's perhaps not quite, I don't know, I don't know enough about the audience, maybe it is in your field, is that I think if we're trying to use these kinds of, I mean, not terribly clever, but reasonably sort of up-to-date, complex statistical methods in ways that will inform routine clinical practice, we have to recognize that it's not enough for the statistician to say, there you are, there's the model, there's the inference, it's great. You've got to turn it into software that user communities need, and that's where informatics comes in, and that's why I think statisticians working in this area need to work with computer scientists, machine learners, and have a kind of multidisciplinary team so that you can follow through these methods to something that will actually sit on a decision maker's desk. And we've got a bit further with that in my second case study than in my first, so I'll move on to that. This is about gastrointestinal disease in the UK, and again the numbers are really just there to show a lot of people suffer from gastrointestinal disease, commonly known as food poisoning. Okay, and those numbers are certainly a gross underestimate, because most people who suffer from these infections just live with it for a few days and then go back to work or wherever. But from a public health point of view, you'd really like to know what's going on with these diseases, and in particular, you'd like to know whether what's going on is just what goes on or whether something unusual is happening. Okay? What you tend to get in this area is very well publicized cases of the pathogens that are relatively rare but potentially very serious, and I'm sure you'll have seen at various points in newspapers headlines about an outbreak of food poisoning which somebody traces to a butcher's shop or a restaurant or whatever. But there's a more insidious, and in terms of public health cost, much bigger issue about people who suffer foodborne disease, which is not serious enough to threaten their lives, but certainly incapacitates them, takes them off work, generally, is costly in a public health sense. So this is really a trip down memory lane, because we started doing this more than 10 years ago. We ran out of money, and my excuse for still talking about it is that we've now got more money and we're picking it up again. But the proposition here is that if you look at specifically, if you think about the date, calls to NHS Direct, which is was the UK's 24/7 nationwide phone-in triage service for healthcare, you could see that people phoning in with symptoms of foodborne disease, the pattern was largely sporadic, necessarily concentrated where people live, but occasionally you got what looked like clusters of cases. I've put clustered in inverted commas here because it's actually a term I don't like. The term I prefer is anomaly, because you can see there's a characteristic pattern, and what sometimes happens is something surprising happens. Now, surprising is an important word, because surprising means you wouldn't have predicted it, which means it was uncertain, which means we're back in the realm of probability being the formal language with which to address the problem. And the challenge we were given back in about 2000 was, can spatial statistical modelling enable earlier detection of these, quote, clusters, unquote. So the approach we took was to say, okay, what you see is what you expect, conflated somehow with what you don't expect, and when you're modelling risk of disease, the natural way to conflate two things is to multiply them. So we're saying there's a background risk, lambda naught of x and t, x being space and t being time, And we multiply that by something we don't understand. And because we don't understand it, it's stochastic. Stochastic is a metaphor for our ignorance about what's going on. And it allows us to express the unexpected part in probability terms. And so the idea is really an exact analogue of what we were doing with the kidney patients, except it's now in a geographical setting, and it's not following individual patients longitudinally. We use the incident data up to time t to construct our best guess, prediction of the current risk surface R, and in particular we express our uncertainty about that best guess through probability. And we identify what I call anomalies, which you then might want to follow up. Okay. And as I said earlier, there's a strong vein of pragmatism running through these things. You've got very messy data. There's not a lot of scientific theory to guide you how to build a model, so you tend to build empirical models, and those empirical models very often rely on unobserved random variables being Gaussian. So you can clearly, if you look at the first equation there on that page, and you're not a statistician, you will say, well, that's ridiculous. All you're saying is you can write a function as a product of two other functions. But if you're a statistician, you'll understand the crucial difference is that lambda is a parameter and R is a random variable. And you have to still add something more to it to make the problem well defined. And what we say is that we expect to see spatial variation in risk because of things like population density, lifestyle, wealth, all sorts of things. We expect to see variation in time because foodborne disease has a peak in warm weather. What we don't expect is those two things to interact, not on the scale we're dealing with, which is a single county in the UK. They would interact on a larger geographical scale, but I don't know if you've been to Hampshire, but it's not the most exciting part of England. You know, if I put you down in Hampshire and took your blindfold off, you wouldn't know where you were, except you're in Hampshire. Okay? It's not a very heterogeneous environment. But things that we don't expect could indeed be both spatially and temporally localized because of common causes. Right? So the R has to be genuinely an interacting function of x and t, whereas what we expect, the lambda naught, can be a product of a spatial effect and a temporal effect. And we now have very different data than before because instead of having measurements of something, we've just got a point process of places and times at which events occur. But the common underlying theme is that what is driving that process is an unobserved Gaussian process. Back in 2003, in order to estimate the baseline spatial variation in risk, we just put a kernel smoother over our historical accumulated series of data. At the time, NHS Direct was a brand new service and we had no idea how representative its usage was for the population. So we didn't feel inclined to use population numbers as denominators. I think now that we're redoing it, we're going to have a more closer look at using population denominators adjusted for things like socioeconomic status. But the point is that it's a very peaked surface because most of Hampshire's empty, or it's a national park or national forest or something. And there's very strong concentrations in the urban areas necessarily. What we saw in the time trend, this is now aggregating over space and looking at the time trend of calls, is the seasonal peak that's well known by people who study foodborne disease, and also a rising trend which is almost certainly to do with this progressive uptake of a new service rather than any underlying trend in the biology. And we did later look at an extension for the next year, and indeed it leveled out. But for the purposes of the data I'm fitting, we fitted that model. We then looked at whether we were capturing the residual covariance structure reasonably well. This should ideally be, of course, a perspective plot rather than looking at the two margins. But what I'm trying to convey to you there is that we capture a spatial correlation which says this is pretty localized up to about 1 kilometre. And if you're thinking about something that's got a common origin in a reasonably urbanized environment, that's about the right order of magnitude. Now, in the rural areas, 1 kilometre probably you might not even have a neighbour next to you, but most of the population we're dealing with in Hampshire live in towns and cities. In terms of time, you can see that we're talking about correlation over a period of order of magnitude up to a week, and that's about right for acute foodborne infections. Doesn't mean it's a good model, but it means it's not demonstrably a bad model. Okay, and so then we turn the handle. And the handle in this case is a little bit computationally harder because we can't write down explicitly the predictive distributions we're interested in, but we can simulate from them using Markov chain Monte Carlo. And what we then do is say, okay, what the clinician wants to know is whether things are elevated to a level that will be practically significant. In other words, so the question we asked our public health colleagues at this point was, would you get out of bed in the morning if somebody told you there was a doubling of the local risk? A quadrupling, an octupling? You know, that's the kind of level at which you might say, okay, we need to intervene. But you have to tell us what C you want to use, and based on that, we'll tell you how likely it is, as a function of space and time each day, whether that threshold has been exceeded. And we got daily updates implemented on a website back in the early 2000s. We got the data from Southampton at midnight, which triggered an analysis which updated the web page in the morning. And the kind of maps the web page had were like this. And that's a particular day I've shown you where something is happening. But it may seem callous, but what roughly happens with these things is, if there is a rise in incidence, then in crude terms, the point estimate of the relative risk is huge, right? Because on average, none of these pixels should have a case any day. So even one case empirically is large, and two cases is out of sight on a point-wise basis. So you really are not terribly interested as a public health physician in transient doublings of incidence. But I put it there so you can actually see some structure on the map, and also to emphasize that the color scale for the map is deliberately chosen so that it's mostly green most of the time. So we only really start getting some interesting color when that predictive probability that there is a local doubling at least of risk gets up to about 95% or more. And the dots are just a 5-day moving window of the most recent case reports. And if you tamp up the level, you can see that most things disappear, which is what you would hope, because if we were signaling outbreaks all over the place, there would be something seriously wrong with the British public health. Okay, now if you fast forward to now, we got another slug of money to expand this to national coverage, and really quite interestingly to integrate human and small animal veterinary surveillance to see if there's any cross-infection between pets and their owners. And then we hit a political problem, which is that the government, I almost said the Tories, that was very unkind, it was Nick Clegg's fault just as much. The government canned NHS Direct, and they wanted to be market efficient, so they put out local services to tender. So instead of having a single national service, we have a multiplicity of local services, some of which are very good, some of which are not very good. So we couldn't get data. As of last Friday, we've been assured we can now have national data, but now we hit an ethics problem, which is that having emphasized from the start the success of the prototype relied on us being able to finally resolve the locations of calls because the correlation structure is small scale. For ethical reasons, we're now told we can only have postcode areas, not unit postcodes. For the non-Brits in the audience, of whom I hope there are many, the UK postcode system, what's so-called full postcode in the UK, will go down to the individual street level. But you can actually get coarsened versions of that postcode, because my postcode is LA13AQ. And that will identify my street. You know, when I want to buy something online, I put in LA13AQ, and they say, what number Meadowside do you live in? If you just get LA13, that's a larger area. If you just get LA1, that's larger still, blah, blah, blah. And we've been told we can have LA13, but not LA13AQ. So from a statistician's point of view, that's of course nice, because it means you've got to work harder again. So what we now want to do is to fit these spatially and temporally continuous point process models to spatially degraded data, which are just counts in regions, which is, you know, quite a nice problem. But the principle is still going to be the same. Now, the vets are way ahead of us because nobody asks cats and dogs if they object to their data being made public. So I just thought it was worth diverting from my talk to show you the current state of the veterinary version of this, which I think is on my Chrome page. Let's have a look. Maybe, oh no, it's not, beg its pardon, that's the wrong one. It's on the internet for some reason. This crappy thing, yeah. Okay, so this thing is called SAVSnet, Small Animal Veterinary Surveillance. And this happened before. For some reason, it seems to want to go to Iceland, but there it is in Britain, right? And each of those dots is an animal currently being treated. And when the vet hits the diagnosis, you get this flag coming up saying, yes, that's one. Oh gosh, that's bad. That's a dog that's not got long for this world. And that's as it's happening. Those data are permanently being fed through, and this really is in real time. I mean, it's a moot point whether knowing that it's being treated at 10:53 rather than sometime today, but that's a separate issue. But what I like about this website, because I didn't write it, is that there's a statement at the bottom which says, and I quote, to fully understand these changes, it is essential to apply complicated statistical modeling. Right? And so the point is very much, as in my earlier examples, these are data, but those data are concealing an underlying signal, which you hope is pretty flat. But if just occasionally there's an upsurge in dogs and cats presenting with gastro-intestinal illness, you might be concerned of the possibility of some cross-infection. And so, apart from being interesting in its own right to dog and cat owners, and certainly to the vets who've signed up to this, because every dot in there represents a vet practice that's signed up to this system of triggering in their data very easily. They need to hit 3 buttons, I think, to get their data recorded. We're hoping to integrate the human and the veterinary data. But again, the other nice thing about this is that these guys are way ahead of me, certainly, and probably most of my colleagues, in terms of the nice software they can write. Well, they're not way ahead of Barry Rowlingson, if those of you know Barry, but everybody else. But they have no statistical modeling capacity. And so there's definite complementarity to what we can bring to that problem. Okay. Right. So we've got to recalibrate the AEGISS model, and as I say, we've got to fit these spatially continuous models to spatially discrete data. The joint modeling of the human and animal incidence will be interesting. I'll be surprised if there's a very strong cross-dependence, frankly, but it's a proposition worth looking at. And critically, if you want anybody to care, it's not good enough to have a fancy web page on a university website. You've got to actually get it into practice, and the vets have done a great job in recruiting, the academic vets have done a great job in recruiting vet clinicians to be part of this system and to see its value. Okay, final case study. The point about this picture is to point out that in many settings in the developing world, you cannot expect data to be collected to a strict paradigm with a perfect design. Resources are extraordinarily tight, and you have to get data where you can get it. The guy on the motorbike is a field epidemiologist, and he's on a 4-week field trip. And he started off driving a Land Rover, and when the roads ran out, he unhitched his motorbike from the back of the Land Rover and carried on, because he'd got a list of villages he had to find and take blood samples from to help us map prevalence of, in this case, not malaria, in this case, river blindness. But it's a very different world. But I would say, although I'm not going to say anything about it in the talk, that a lot of the people in that village will have mobile phones. And so there's a real opportunity for mobile technology to penetrate into extraordinarily poor and remote communities. And that has a big potential, I think, for improving the healthcare in these communities. But that's a little bit of a sort of evangelical sideline. I'm not actually going to talk about it. I almost cut these slides because they're so simple, but then I thought, well, no, I mean, I've never yet gone away from the talk thinking, God, I wish that was more complicated. So I thought I'd just take you through how a statistician thinks about prevalence mapping really from square one. And if you think I'm talking down to you, I can only apologize. Right? But what do you mean by prevalence? Well, what you mean is if you've got a sample of n individuals who live in one of the villages that the chappie on the motorbike eventually got to, and you test them for disease, and y of them are positive, then Statistics 101 says that y is a realization of a binomial distribution with number of trials n, that's the number of people you tested, and probability of success, p, is the prevalence, the proportion in the community at large that are infected. Now, you then get back on your motorbike, you go to another village, and a third, and a fourth, and a fifth, and eventually you've got data from m villages. So Statistics 101 says, no problem. The yi's are binomially distributed with ni individuals and probabilities pi. But there's a problem now, because as soon as you measure more than one village, then you can start thinking about how do these villages differ and what are the heterogeneities occurring between those villages. And again, in parallel with something David was talking about, you can model heterogeneity in statistics by either measured risk factors or covariates or explanatory variables. These things go under a number of names, which in this case I'm using D for that. That's David's X, it's my D. And you can also say there are unobserved characteristics, right? And we model those as random effects, U. Okay, so when we're looking at all these data together, it may be that the big Ys are coming as a function of things we can measure about the communities, their general wealth, what the prevailing environment is, in the case of malaria, how many mosquito breeding sites there are nearby. But we can also recognize there are heterogeneities that we can't capture in our measured data, so we model those as random effects. But then the question is, well, what do you do if these things are spatially structured? In other words, they have a geographical pattern to them. Well, for the Ds, it makes no difference. They're just things you measure. But for the Us, it does. And the Us then have to be replaced by, surprise, surprise, a Gaussian process. So we're back to the same paradigm as before, which is that the things we don't understand, we model as a Gaussian process, which in this context we expect to be spatially correlated. Okay? But there will also be spatially independent random effects, because two villages can be close together but have completely different social structure. Okay? And that would affect things. So it's not just a function of space, it's a function of other things as well. And then you just build the standard statistical regression model, which is a logistic model. Doesn't have to be logistic, but that's the standard default option. But now with a pair of random effects, a spatial one and a non-spatial one, and off you go. Now, in view of the time, I'm going to skip this slide, but all that's saying, for those of you who recognize that that is just a DAG, a directed acyclic graph, if you've got different kinds of survey instrument, you can still combine these into a more complex Gaussian process, but you have to recognize that some data are more precise than others, some are more noisy than others, and you have to be a bit careful that some survey instruments might produce biases, B for bias, but I'm not actually going to go into that anymore because I want to get us roughly back on track for timing, as I'm sure Neil would like me to do. So instead, what I'm going to do is just show you what we do with this stuff in the Chikhwawa district of Malawi. Oops, I should have gone down, not up. So that gives you a sense of the geography that we're dealing with and where we get our data. And you can just see a river running down from north to south. This is a rural area near Blantyre, Malawi. And it's an interesting study area, and it is indeed a permanent field site set up by the Liverpool-Malawi Wellcome Consortium, because it's very heterogeneous, both in terms of its natural environment. It goes from a kind of dry plateau down to a very swampy plain, and also its socioeconomic variation. So that in terms of both lifestyle and natural environmental factors, there's a lot of variation in risk in what is actually a relatively small area. That's what, 0.7, that's 0.2 degrees of longitude, which is about, 20 kilometers, I would guess. So what I want to do is say that using this stuff and getting data monthly, remember I said that sometimes real time is very slow, you can see predominantly here there's a very strong seasonal pattern of malaria. Okay, what we're looking at here is basically areas that probably have greater than 20% prevalence. And you can see that very strong right to left contrast. And it's basically the river, which is flat on the left bank and goes up. Sorry, no, the plain is just on the right bank where the red spot is. The plateaus are to the east and west. Okay, and we followed that through, and it's almost done. And we've used this in actually giving presentations to the communities, because what you can do, having shown that, which, I mean, they all know that malaria is seasonal, but quantifying it is quite interesting. And if you then go, let's see if I can work this, I'm not the best at this stuff. There's May 2013, and that is the high season for malaria risk in this part of the world. And you can see that there is this hotspot to the right of the river, okay, which is essentially a floodplain. And if you go back to 3 years earlier, you can see the difference that community interventions of various kinds have made in 3 years, and that's a very powerful message to the local communities. We're now doing a similar exercise in another part of Malawi, where they're trying to develop as a major tourist attraction, a national park, and people are not going to go to national parks if they're afraid of getting malaria. So the green area here is the national park, and all around the park there are communities which at the moment are pretty undeveloped and have pretty poor healthcare, and we're actually embedding within our monthly monitoring a randomized trial of community level interventions to try to reduce malaria. And I've put that slide up mainly because there's quite a nice, this again is really just for this, well no, it's not just for the statisticians, it's for anybody who likes puzzles. There's quite a nice design problem in this randomized trial, because every community wants to take part in this study, because there are 4 treatments in a 2 by 2 factorial arrangement, but all of them include some remedial measures. So all the communities want to be part of this trial. The problem is that, firstly, in order to not enrage the clinical trial pedants, you have to randomize everything. But secondly, because mosquitoes fly, you can't randomize adjacent villages to different treatments. So we have a constraint based on the estimated flight range of a mosquito that says that any 2 villages that have homes within that distance have to be randomized to the same treatment. And when you do that, the geometry gets quite complicated. And in particular, if you're not careful, if you just sort of eyeball it, you can end up with very few randomization units. So the guys in Malawi, who are very bright people but not formally trained in design theory, flailed away with pictures and pencil and paper for a couple of days and came up with a design. Me and my colleague Emanuela Giorgi, who are statisticians, said, oh, we think we can do better than that, and set up a Monte Carlo experiment just to try millions and millions of designs and see which one was best, and felt very pleased with ourselves when after 6 hours we got a better result. I then went home that evening, and my partner is a graph theorist. It took her 20 minutes to beat both of us. So the mathematician actually beat the statistician at producing an efficient design under constraints, which you can formalize as a network, you know, and you've got basically paths in the network that you're not allowed to cross. Okay, so that's it really. One thing that I'm borderline obsessive about is trying to get across the message to policymakers that the right way to make decisions under uncertainty is to decide what would make you make a decision and try to quantify how likely that condition is met. And then you can have an informed debate about costs and benefits of doing nothing or intervening. In other words, as it says there, to inform but not to override clinical judgment. And I think there are interesting still methodological issues here. Almost invariably in this area, I find myself dealing with observational studies rather than trials. That last slide was an exception. And there I think you have to be aware that the best is often the enemy of the good. And you need to compromise between what you would like to do and what's feasible. And I'm a great believer in Tukey's dictum that it's better to give an approximate answer to the right question than a precise answer to the wrong question. And in these messy data sets, often you make heroic assumptions, you have to put caveats in your conclusions, but I do think that modeling the process in this slightly cavalier way is justified when you're wanting real-time answers to complex problems. And the really interesting methodological challenge, I think, is thinking of all of these problems as marked point processes, because we don't design those locations, right? Nature gives us them, and therefore we've really got to think of this as a joint stochastic system of points in time, space, or space-time, which are stochastic, and measurements made at those points, which are also stochastic. Okay, thanks.